Okay. Let's now talk about some interpretations of probability. So we've talked about how with conditional probability, we are thinking about essentially narrowing the scope of possible outcomes down to the event that we're conditioning on. And that's a reasonable intuition to have. There are also a couple of interpretations in the so-called frequency and Bayesian interpretation. So um, let's discuss. Okay. So a technical way to do it, or one way to do it. Whoa, sometimes this thing doesn't really behave. Okay. So we already talked about one. One of them was uh, update the sample space, or we're narrowing the set of possibilities. Okay. Okay. Now let's talk about frequency interpretation. By the way, with frequency interpretation, or I'm sorry, with conditional probability, it's under the assumption that you're conditioning on an event happening, but the event doesn't actually have to happen for you to compute the probability, right? So it can be, in some sense, it's like a hypothetical. You could say, suppose A were to happen, how would that change my opinion about B? Okay, we'll see. We'll see how that plays out, and we can play that out in the frequency interpretation. So remember, in the frequency interpretation, we're imagining that we observe outcomes from P repeatedly and indefinitely. So what does that mean? So what that means is we're rolling dice indefinitely, as many times as we possibly can. We're going to observe that one process repeatedly. Okay. And let's let, it's crazy, does whatever it wants. Let NA, N sub little a, is going to be the number of times an event A occurs in little n trials. We'll write n sub b to be the number of times that B occurs in little n trials. N sub A intersect B to be the number of times both A and B occur in those n trials. From the first lecture, remember, from the first lecture, the ratio of n sub A over n, so the number of times A occurs in n trials, if we then take n to be very, very large, this ratio converges to probability of A as n goes to infinity. So this was from before. That's kind of the traditional frequentist interpretation. And one thing that we can say is, we can say, well, n sub A intersect B divided by N sub A. What is this? This is the fraction of the time that B occurred whenever A occurs. Okay. So let's just imagine we have kind of trials. So trials or rolls or spins, however you want to think about this process. And we're doing this as many times as we possibly can, but it's indefinite. And then we let's mark down whenever A occurred. So let's say A occurred here, 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 here. And then we mark down for each of the same trials. We can ask whether B occurred. So it's like saying in craps or in dice, rolling dice, we can ask, did the dice roll add up to 6? That would be A, for example. And then event B, we can say, was one of the two dice a value of 3? Well, it is possible to get 6 when there's a value of 3, but neither one implies the other, right? So you can ask the same question. So let's say that B occurred here, 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 and here. So then we can ask, well, did A and B occur? Well, this is implied by the first two, right? So A and B did not occur in the first, did not occur in the second, but did occur in the third, right? We have to have an occurrence in both. It occurred in the 6th and it occurred in the 8th. Okay. What we're doing when we compute this ratio here is we're narrowing the scope of trials down to say, I only want to count trials that A occurred to begin with. So I'm going to ignore everything else. So in other words, I'm only going to consider this trial, this trial, this trial, this trial, and this trial. Right? I'm throwing away anything. If A didn't happen, I'm acting like if A didn't occur, I'm acting like nothing, that it didn't even happen. I'm moving on to the next one. Okay. So now if we think about this, so one way to think about the frequency interpretation is that if N is large, so if we have a large number of trials, then the ratio of N sub beta N is approximately the probability of A. So now let's consider, what about if N is large? N over N, the number of times, the ratio of the number of times the intersection of A and B occurred to the number of times A occurred. Well, what do? One thing we can do is we can divide top and bottom by, let's divide top and bottom by N. Sorry, this should be N. So then if we divide top and bottom by N, then by this interpretation, what is the top is approximately probability of A intersect B. The bottom is approximately probability of A. Which is exactly how we've defined conditional probability. This is how we've defined the conditional probability of B given A. So that's one way to recover conditional probability from the frequency interpretation. It's much more direct in the frequency interpretation. The Bayesian interpretation is another interpretation of probability. We won't spend a lot of time on it in this course, but it's something that's important to be aware of. It's worth being aware of, but it's also worth noting that a lot of stuff that's called Bayesian, I want to avoid getting too far on a tangent here, but the word Bayesian gets used to mean this multiple different things. Okay. And what I'm talking about here is that it's an idea that so in the frequency interpretation, the probability represents a frequency, long run frequency, how often something's going to occur in a large number of trials. In a Bayesian interpretation, that's not the case. The way that probability is interpreted there is it's as if it's your belief of how often something's going to occur. It's a subjective opinion. Okay. Now, when you take it as a subjective opinion, then what does conditional probability mean? It means that it's a rule, or it's an idea for how to update our beliefs that about B, given based on the information that A occurred. Okay. So it's a more subjective interpretation. The formula is the same for conditional probability, so that doesn't change. It's just an interpretation. It gets into philosophy. It's not something we're going to spend a lot of time about in this class, but it's definitely something that is worth being aware of. So those are some interpretations. And then we're going to come back. We're going to continue to use conditional probability. Conditional probability is really the key to most probability and most statistics applications of probability, if you think about it, because the whole premise of using probability and using statistics in real world applications is that we're constantly collecting new information. We're constantly observing new things. And it's pretty foolish to have an opinion about something, observe something new, and then just ignore it and continue to have your old opinion, right? So in order to have a reliable framework or a robust framework, we need to be able to ingest new information and update accordingly. That's the whole premise of what statistics is, and and the fact that it can do that is what makes it so useful. So conditional probability is going to be an important topic throughout the course, and we're going to continue now in the next section. We're going to talk about some applications, some examples, and some other important consequences of conditional probability.